like I say, you're going to need a C development environment, and you're eventually going to need an Intel processor. In fact, you're probably going to need it right away. So let me go back to here. And I think you have a previous project that shows you how to do that. Somehow my pages are gone. 142 projects. Yeah, here's your Linux virtual machine. And there are instructions here to create a machine running on an emulated Intel processor, even if you're on the Mac M1. You can't use VMware, you have to use UTM, which is a front for a program that can emulate a different processor. So I do not want to use the machine I was using earlier, which is ARM. I'm going to turn that off. All right, and now I'm going to go and start UTM, which is here. And UTM has let me emulate an Intel processor on my ARM machine. So I've got headless Linux running on it, which is the only thing I recommend doing. Anything with graphics is going to be painfully slow in this emulated environment. And you might be able to see that even this is slower than the other one, but it's acceptable. All right. Got to wait for it to finish booting up. There it goes. Linux always prints a bunch of messages booting up. And usually some of them are errors. You get used to it. Windows does the same thing, but they conceal it from you to avoid scaring the user. Has zoom, makes it even slower, but there it is. Okay, it's moving. It resized the screen, it changed the font. Now it's going to print a bunch of messages. All right, there we are. Oh, that's because this has Splunk installed on it. Holy cow. That's a really bad idea. That's why it's so slow. I'll have to get that off of there. See if I managed, looks like I did not manage to type this in correctly. Okay. Okay. Now, it's not ready until I see a $ prompt. There I do. Now I can do IP space A, and I get the IP address. Now I can open a terminal and do SSH. Student is the username on this machine. And it's 192.168.64.9. All right. Good. All right. Now, I do have a directory already for this. All right. So I've made a machine running an Intel processor, which is the first start for this. And now I just need to install these things. I've already done it on this machine. Build Essential means you have the C compiler. Multi-Live means you can compile for multiple versions of the processor, including other ones than the one you're actually using. And you can run software, 32-bit code on a 64-bit machine. Windows lets you do this by default. Linux does not. You have to install this Multi-Live library in order to do it. And GDB is the debugger, which we're going to use to see what's going on at the binary level. So now I'm going to this hello program, which I think I've already got here. Yeah, there it is. Here's the hello program that just says, what is your name? Uses scanf to read it and then prints it. Notice the scanf does not need the ampersand here because name is an array. And the name of an array is automatically a pointer to the first byte in that array. So I can compile this various ways. Now I've already compiled it here, but I'm just going to remove the compiled version and compile it again so I can control it. So what we're going to do here is we're going to compile it with no stack protector. This will make it possible to do a simple buffer overflow, which is otherwise blocked by a security feature in modern operating systems. We want to deliberately compile it the old-fashioned way, where it's more vulnerable so we can practice attacking it. So it asks me for my name. My name is Sam. It says hello, Sam. So that's fine. If I give it a long name like this, and notice there are no spaces in the name because a space would terminate the input. So if I run it and put in this name, then I get a segmentation fault. This is very bad. This means it tried to access memory that was not reserved for the use of this program. And that is that is an indication of a buffer overflow, or it can be other flaws. But in this case, it is a buffer overflow, and you can see that with the debugger. If I run the debugger in quiet mode, just to avoid having a bunch of junk on the screen, it's going to let me see what's going on when I run the machine. So I run, it's going to ask me a question. And when I'm going to give it this answer, instead of putting in Rumpelstiltskin, it's better to have a non-repeating pattern that you can easily understand, and you know what it is in ASCII. Capital A is 41 in hexadecimal, B is 42, C is 43, and so on. So it's easy to take the raw bytes and understand which character caused it. And notice this, 45, 45. That's EE. So some of the characters I put in ended up in the instruction pointer. And you can tell if you do info registers, you're going to get used to these registers. They're going to be your best friend. The registers are little locations on the processor that store information about how the processor should run. There's temporary scratch pads used for everything, and anything you care about for longer term, you move it out to memory or put it on the hard disk. And the most important register here is going to be RIP, which will come down here. There's RIP. RIP is the instruction pointer. That's what controls which instruction is next. And the goal of the attacker is typically to gain control of RIP, because then I can control the machine. I can redirect execution to a different command than what the developer intended. And you can see some of the characters I typed in have ended up in RIP. And that's the essence of how this is going to work. And we're going to do this a lot more as we go ahead. But that's all you have to do for your first one, is get your environment set up so you have the compiler, the ability to compile in different architectures, and the debugger. Then you're ready to start seeing how programs work at the binary level. So that's it for that one. Let me stop this recording.